Good morning. Um, we are headed into some different topics. We're headed into chapters 27 and 28. And chapters 27 and 28 are going to introduce us to magnetic forces and magnetic fields. Now, the title of the chapter they've got here is Magnetism. I think I want to cross that out. So let's cross out magnetism, and let's put in magnetic forces and magnetic fields. Maybe I'll go back and make that change in the notes. Because magnetism, I don't know, it doesn't carry the same feel to it. Anyway, what they're showing here, this is supposed to be a representation of the magnetic force. So what they're showing is that here is a wire with some current running through it. And if I've got a wire with some current running through it, those are charges, and they're in motion. It turns out that when you have charges, you have electric fields. We've seen this back in chapters 21, 22, 23. If those charges go into motion, then in addition to the electric fields, you have what we call magnetic fields. So that's what this picture is indicating. Now, when you think of magnetic forces or magnetic fields, the first thing you think of are magnets. And you would think, I'll bet magnets are somehow the foundation or the most fundamental way we can approach this, and they're not. It turns out that everyday magnets that you play around with are actually at a fairly moderate level of complexity. And so it's not really at the basis of what's really going on with the magnetic force. In any case, we probably have to address the issue of what are magnets and how do they work. And you may be familiar with magnets in that for a bar magnet like this, they're usually labeled as having like a north end and a south end, having to do with whether or not they would orient themselves with Earth's magnetic field, and then one end of the magnet would point to the north, and one end of that magnet would point to the south. Now, what you've also probably heard, which is accurate, if you take the north ends of magnets, they repel each other. If you take the south ends and orient them towards each other, they are also repulsive. But if you take a north end and a south end, they're attractive. Now, at first, what this sounds like is plus and minus charges, but it's not the same thing. And what we'll find out is that magnetic forces and magnetic fields depend on charges, the same as electric fields do. The north and south is something different, so let's take a look and see what that is. First of all, let's go in and just generally write down what do electric fields look like surrounding charges, and what do magnetic fields look like. Now, for a charge doesn't have to even be in motion, but if I have a charge that's either at rest or at constant velocity, that isolated charge, that charge will have an electric field. And the electric field is given by kq over r squared. I'm hoping some of this feels kind of familiar. This is something we saw back, I know it was like chapter 21, right? It's like 6 chapters ago. But the electric fields, for a point charge, kq over r squared, and then we had these little unit vectors that we had introduced as a way to keep track of the direction. So what this formula is telling us is the electric field is directed radially away from positive charges and radially towards negative charges, and the magnitude of that field is kq over distance squared, where the distance is measured from the center of the point charge, the point at which that charge is located. Now, there's no angular dependence, so I put the angular dependence in here just to say I could be looking in different directions, but in the limit where the velocity of the charge is relatively low compared with the speed of light, to a very good approximation, the electric field remains having the same magnitude in all directions. Now, what we said was magnetic fields and magnetic forces begin to show up when the charges are in motion. So if I take that very same charge, some very same point charge of Q, and we have it moving, in addition to the electric fields that we've already outlined, we're going to have magnetic fields. Now, for historical reasons, a couple things we have to get used to here. First of all, the electric fields go by the symbol big E. And you go, that makes sense. Electric field, capital E. Sure, that makes sense. Magnetic fields, for magnetic fields, we use the symbol capital B. Not sure what that connection is, but anyway, magnetic fields are capital B. Now, for historical reasons, the units that we use for electric fields, newtons per coulomb, are not the units that we use for magnetic fields. It wasn't my decision. If it was my decision, we go back and use the same units for both. But fortunately, there's an easy fix. If I want to do a direct one-to-one comparison between electric fields and magnetic fields, I just have to add a factor of c, which is the speed of light, 300 million meters per second. Now, what is the speed of light doing in formulas related to electric fields and magnetic fields? And what we find is the physics that we've been doing up until now is based on the assumption that we have 3 dimensions of space and 1 dimension of time, and that time is independent from the 3 dimensions of space, and that means that time progresses at the same rate everywhere. It turns out that's not quite true. You may be familiar with ideas from special relativity, which we'll be seeing in a few weeks. It's not that far off. It turns out that space and time are actually interconnected, and that what we call the speed of light, that little symbol c, is more generally the conversion factor between measuring things in time units and measuring things in space units. I know that sounds crazy, but the reason c shows up in the formula is because of the properties of space and time. Now, it turns out that the gravitational formulas that we work with, that Newton developed, are based on the assumption that time is independent of the space components, which is not quite true. But the electric and magnetic field formulas that we've been working from actually are based on special relativity. So these are some of the formulas that actually led Einstein to start thinking about how space and time might be connected. At first, it looked like kind of a contradiction between what was being observed with electric and magnetic field formulas, and then Einstein was able to resolve the whole issue by showing that space and time were connected. So, kind of an interesting aside, I hope. In any case, electric fields are measured in newtons per coulomb. If we want to measure magnetic fields, also in newtons per coulomb, we have to add a factor of c. Now, the textbook doesn't do this, and so you guys are going to have to be familiar to do it either way, and I'll be going back and forth between these two approaches. But when I'm doing a direct comparison between electric fields and magnetic fields, I think it's useful to put them on equal footing so we can actually see how the formulas compare. So the electric field depends on the electric force constant, the charge, the amount of charge, divided by distance squared. So does the magnetic field, kq over r squared. Now, what's different here is that the magnetic field depends specifically on velocities. And within special relativity, all velocities are measured relative to the speed of light, relative to c, which is our space-time conversion factor. So in special relativity, c is the very fastest speed that is possible because that's the way space and time are put together. There's no such thing as going faster than c according to special relativity. So it's a factor of v over c. And then as far as directions, now the electric field was pretty easy. It was just directed away from the charge, or if it's negative, towards the charge. The magnetic field is sideways. And so what we have is a cross product. Now if you remember the cross products, let's see, I use a right-hand rule. I put my thumb in the direction of the first vector, fingers in the direction of the second vector. So the first vector here is a unit vector in the direction of velocity, and the second vector here is a unit vector in the radial direction. So the new piece of this is this velocity unit vector, and then I do a cross product. And what that tells me is that the magnetic field is coming out of the page and that it loops around. So the magnetic field is not directed away from the charges. The magnetic field forms circular loops. If it's a positive charge, those loops are right-handed. If it's a negative charge, the magnetic field is oriented in the left-handed direction. But in any case, there are these magnetic field lines that loop around the direction that the charge is traveling. So if I say, here's the velocity of that charge right there, then there's a bunch of loops surrounding that charge at all locations. And what this formula is telling us is as we move away from the charge, how much does the magnetic field drop off? Well, it drops off like 1 over r squared. That's exactly the same as the electric field. But there's also an angular dependence due to this cross product. The cross product of unit vectors introduces a sine theta component. Now what that tells us is if theta is equal to 0, there is no magnetic field. So the magnetic field in front of a charge and behind the charge are very low magnetic fields, and directly in front and directly behind the magnetic field goes to 0. Where are the magnetic fields the largest values? At 90 degrees. And so it's actually the loops here. The loops in these regions are the strongest magnetic fields, and then the loops as I get out in front, or the loops that I have when I get back behind, those are not as strong. So with magnetic fields, they drop off with distance, just like the electric fields do, but they have this angular dependence to them also. And the magnetic fields also have a velocity dependence. So it is a little more complicated. There's a velocity factor and there's an angular factor in determining magnetic fields. Now textbooks tend to skip this step because I'm not sure why. It doesn't really seem that much more difficult than other things that we talk about. But this is really at the foundation of the sources for magnetic fields. Now what that says then is that the magnitude of the magnetic field, once I take this factor of C and I move it over to the other side, the formula to tell me how strong the magnetic field is the electric force constant divided by C squared times Q times V times the sine of the angle. And again, it's going to form these kind of loops. So this is a picture we're going to refer back to because this is our foundational, most basic picture. Now what this leads to is a question of, well, what types of velocity could the charge have? So for linear motion, here's a charge, it's just traveling off in some direction. That's what we showed on the page before. And linear motion by itself just produces these either right-handed loops or left-handed loops, depending on if the charge is positive or negative. But there's another type of motion that is really, really important. And this comes down, this shows up not just in, well, it shows up in devices that we design. So we build devices that make use of magnetic forces. And so that's going to be very important for us. Usually when we're building something, in order to generate a magnetic force, the charges are the current running through wires. So we run a bunch of wires around and we run current through them. Anytime we're running current through a wire, it's going to generate a magnetic field. Okay, so currents generate magnetic fields because, hey, currents are charges with velocity to them. But there's also rotational motion to consider. So you could have charges that Well, you could take a loop of wire and you could move it in a circle. That would be charges going in circles. But we also have in nature our atoms and molecules. And what we've talked about over the past few weeks here is that the forces holding atoms and molecules together, and the forces how molecules attract each other and form different solids or form different types of composite condensed materials, they all trace back to electric and magnetic forces. And now we've looked at some of the electric force components. Now we're ready to talk about magnetic effects. And so you may be familiar with the idea that electrons have a built-in angular momentum. It's kind of a crazy thing. Electrons have, they have a certain amount of mass that they carry with them wherever they go. They have a certain amount of electric charge that they carry with them anywhere they go. They also have a certain amount of angular momentum, a fixed amount. It's not like they can spin at any speed they want. There's a fixed amount of angular momentum in an electron. There's also a fixed amount of angular momentum in a proton, and there's a fixed amount in a neutron. The electron, proton, and neutron each have what we refer to as 1/2 unit of spin angular momentum. And so anything that has charge and has angular momentum, that's the equivalent of charge in motion. So anything that has charge and angular momentum will have a magnetic field. So every electron you encounter has a certain fixed amount of spin, a certain fixed amount of charge, and it has a certain shaped magnetic field that we call it a dipole shape. So this is the shape of a dipole magnetic field. Now if you remember, the word dipole traces back to chapter 21 when we were looking at electric fields. And we said if I take a plus charge and a minus charge and combine them, they create an electric field that has a certain shape to it. So when we say that this is a dipole magnetic field, what it's saying is not that we have two different charges, but it's saying the shape of the magnetic field has this dipole shape to it. So the name really comes from the geometry. And all we need is just one spinning charge. One spinning charge by itself will generate a dipole magnetic field. And as you might imagine, if it's spinning one direction, the magnetic field lines are oriented in a particular direction. But if it spins the opposite direction, the magnetic field lines will reverse. So there's always this reversal symmetry if we change the direction of motion. This becomes one of the most important features in analyzing the properties of atoms and molecules, because every one of those electrons in there is going to have a certain magnetic field effect. It's going to behave like what we call a magnetic dipole, and that enables technologies like magnetic resonance imaging. When we get scans of magnetic resonance imaging, MRIs, what we're doing is we're putting the patient in a really, really large magnetic field. And what that large magnetic field does is it flips the available electrons so that they're all spinning more or less in the same direction. And then as those electrons flip back, we can see how they're absorbing or radiating, either absorbing or radiating radio energy photons. Okay, so being able to play around with magnetic fields allows us to move electrons into different energy states, different quantum states, based on their spin. And if you've seen an MRI, it's just amazing the resolution you can get from that, and it's done using the magnetic properties of the electrons and the magnetic properties of nuclei. So the protons and neutrons also have magnetic fields to them. And I think the MRI is mostly based actually on spin properties of the nucleus. So every nucleus in every atom and all the electrons in every atom have some amount of magnetic dipole. They're producing a magnetic field, and they feel the effects of magnetic fields that they are placed in. So it's a two-way interaction that takes place. Now, that's what's going on in our magnet. Why is a magnet a magnet? Now, magnets are typically made out of iron that has been magnetized. What does that mean? And in a block of iron, like most other materials, most other metals, there's some number of electrons that are able to switch their spins back and forth. Now, if all of the spins, if I take a block of iron, the leftover electrons that can spin in whichever, spin up or spin down, whichever state they want to be in, it's kind of a random mix. And so what happens is, overall, there's no magnetic effect. The magnetic effects tend to cancel out. But iron is one of the few materials where I can actually align the electrons and they will stay aligned. And the electron spins. And the electron spins can be aligned by placing them in a magnetic field, a large magnetic field, flipping the spins and then leaving that there for a while, so you can actually magnetize iron. And that's kind of what magnets are. They're permanently or semi-permanently electrons whose spins have been aligned. So next time you see a magnet like that, you go, oh, it's just a bunch of electrons whose spins are aligned. Now what happens if I align all the spins is that I get this reinforcement of this dipole-shaped magnetic field. So what shape magnetic field will this magnet have? That's the shape. That's what it's going to look like. And so what we've got are these field lines that loop around. And to show the orientation of the magnetic field, we label one end north and one end south. Now, one way we can go in and demonstrate this idea is, well, if I take a magnet and I cut it in half, am I going to have a north magnet and a south magnet? And that's not what happens. If I take a magnet that's been magnetized so that it's got this orientation of its spins, and we've labeled them north and south, and I cut it, I now have two magnets, because I will continue to have that same orientation of the spin in both sections of the magnet that have been broken into two. So it's done with spinning electrons. That's what's going on with the magnets, is that we've been able to align some portion of the spinning electrons. The electrons have two possible spin states. We refer to those as spin up or spin down. In unmagnetized materials, those spin states, all the magnetic fields cancel out. But in a magnetized piece of iron, for example, we have created a preferential direction. We haven't aligned all the available electrons, but some portion of them have been aligned. And that's what makes a magnet a magnet. Okay. So that's fairly complicated. So we're not going to do any mathematics in these chapters as complicated as dealing with all of these magnetic effects inside a magnet. Okay, and this is just repeating the same idea. So what would happen if, going back to this picture, what would happen if I took this block of iron and I reversed the direction of the spins on all the electrons? Instead of the preferential direction being this orientation, what if we had a preferential spin in the opposite direction, and the north and south would reverse? So the north and south is just based on which of the possible spin states are the electrons placed in. Okay, we'll get back to that. We may refer back to this again. So north and south, bottom line, north and south are not the same thing as plus and minus charges. In fact, all of the magnetic effects that we see are traced back to plus and minus charge. So when we say this is the electric charge, it's also the magnetic charge. We don't have to introduce anything different from Q. Q is used to determine electric fields. Q is used to determine magnetic fields. So the very same Q shows up in both. N and S, north and south, are just keeping track of orientations. Now here's another common example of where we think about magnetic fields and we go, what about planets? Earth, for example, has a magnetic field. What's the shape of Earth's magnetic field? Well, it's this dipole shape. It's kind of this apple shape, right, that you see. What's generating that? Is it a bunch of electrons deep in the Earth with their spins lined up? And we don't think it is. We think that in Earth's case, in the case of the planet, there are actual currents of electrons. There are currents of electrons and there are currents of positively charged nuclei, and they're not moving through the Earth's core at the same speed. So if the electrons are a little faster, for example, there's going to be a magnetic effect that's generated. If the positive charges and the negative charges are moving together at the same speed, the magnetic effects cancel out. And so to generate this magnetic field of the planet, we would need to have, for example, the electrons flowing through the material at the core of the Earth a little faster than the nuclei are. Okay, that's all it would take. And there are models explaining how, the Earth's got a solid core that's mostly iron. It's got a surrounding liquid core that's mostly iron. And this also is a bit of a complex topic, but we do feel like we have models now as to how the rotation of the Earth results in the continuing formation of these electric currents, basically, currents of charge flowing, and that the magnetic fields become self-sustaining. So, as you may be familiar, Earth's magnetic field varies over long time periods. In fact, every million or a few million years or something, Earth's magnetic field reverses. But it's still self-sustaining. As long as we have the ability for this, I think it's for the molten core, right, that we have. Okay. Anyway, that's a bunch of geophysics stuff, really interesting field, but you can generate magnetic. So in atoms and molecules, you can generate magnetic fields due to the spins of the electrons, spins of the protons, spin of even the neutron, because the neutrons made out of quarks, which are charged, so even the neutron has a magnetic field. And then also because of the orbital motion of the electrons. So depending on what the pattern of electrons is, there are these different quantum states. Different quantum states within the atoms and molecules will also produce magnetic fields. So the magnetic fields, they're going to be there. We're going to have these magnetic fields in atoms and molecules at the smallest scale, and then at this very large scale with planets, or like the sun, stars produce enormous magnetic fields. So recently, from right now, just last week, we had some huge solar flares, and these eruptions, are generated through magnetic effects. So magnetic effects are pretty important. All right, let's move on. We haven't seen anything numerical. You haven't plugged any numbers in any formulas yet. So how do we get a uniform magnetic field? Now what you can do is you can produce some blocks of iron. They're not showing the whole thing here, right? The iron probably wraps back around and the iron's magnetized, and we're trying to produce a region here where we have a uniform magnetic field. Here are a bunch of compasses responding to the charges that are in motion. So when we have a bunch of charges in motion, what we're going to end up with are those right-handed loops in the direction of the charge that we've defined as the current. Now in reality, the electrons are going the opposite direction, but currents are defined as if it was positive charges moving in this direction. And so we're going to get these right-handed loops, and it's just showing that we're observing that there is a magnetic field set up because these compasses, which are also magnetized, are responding to the magnetic field being generated in that wire. Okay. Now we can take the wire and we can turn the wire into a circular loop. So what happens if I take a wire with these loops, these right-handed loops, and then I turn the wire itself into a loop? Then what I've got are a whole series of right-handed loops all the way along the length of that wire, and that gives us a dipole geometry. So if I have, this is getting back to the Earth again. Let's see. So if I have circular loops of current within the planet, then I'm going to generate this dipole-shaped magnetic field. There's not a big bar magnet inside the Earth, but the field is it's a very simple geometry. It's this dipole geometry. So it does appear to be currents that are following some sort of circular path on average. Now the magnetic field, also what's interesting, doesn't line up with the rotational axis. It's shifted by, what is it, like 15 degrees or something like that? It's shifted a fair amount. So however these currents of charge are in motion, they don't quite line up with the rotational axis of the planet. All right, so we can generate different shaped magnetic fields by using loops of current. So kind of the big picture with electric and magnetic fields is that to determine what the electric field looks like, I need to know how much charge I've got, I need to know how fast the charge is moving, and it turns out the acceleration will also create additional effects. So it's not just the charge's velocity that's important, but the acceleration will also help determine exactly the shape of the electric and magnetic field. So both electric and magnetic fields can be thought of as functions of, and I didn't write distance and angle or whatever, but the fields are going to depend on charge, they're going to depend on velocity, they're going to depend on accelerations of those charges. So for example, here is a charge. I'm going to call it Q1, and it's traveling in this direction. Now if I have a charge traveling in this direction, what I'm going to have are these right-handed loops oriented around the direction of motion. And on a page like this, it becomes a bit of a challenge to draw a picture because the magnetic fields inherently require 3 dimensions. If I'm going to have something traveling here and something looping around, I've got to have a way to represent all 3 directions, all 3 dimensions. So one way we could do this is say, all right, the charge is going this direction. The loops are going to be represented with little circles. These are X's and O's, I guess. So the little circles, the O's, represent where the magnetic field loops come out of the page, and then they loop around and form circles, and then they re-enter, they go back behind the board, and to show where they've gone back behind the board, we draw little X's. So the X's are where the magnetic fields are oriented into the page, the O's are where the field is coming out of the page, and then you have to imagine the loops being completed. Okay? So if I start here and follow a magnetic field line, it's going to guide me around and send me back into the page here. Now I don't want to drill into the wall here, but we could follow the magnetic field back behind the wall, and then it would come back out where that O is up above. That's what these diagrams are keeping track of. All right? Okay, so any questions? Stop by office hours, we'll get those looked at. Now, when I think in terms of charges, and I've got these charges here, Q1 and Q2, what we have to remember is that charges are going to create or generate electric and magnetic fields. So charge 1, for example, is going to generate electric field 1, that I have listed over there, and it's going to generate magnetic field 1. So I've got a formula for the electric field and the magnetic field, and I've tried to draw a picture here keeping track of all of this stuff. The electric fields are directed away. The magnetic fields are forming these right-handed loops because the charge is positive. And Q2, this other charge, will feel the effects. So charge number 1 generates electric and magnetic fields, E1 and B1. And then charge 2 is going to feel the effects of those. So charge 2 will feel a force due to the electric field from charge 1, and it will also feel a magnetic force due to the magnetic field of charge 1. Okay, so yeah, it gets kind of, it gets a little crazy here, huh? Now the force that charge 2 experiences is going to depend not only on the magnetic field from charge 1, but the force that charge 2 experiences also depends on its own velocity. So for these two charges to exert magnetic forces on each other, they both have to be in motion. If charge 1 is in motion, it will generate a magnetic field. In order for charge 2 to experience that magnetic field, it needs to have its own velocity. And finally, remember that the velocities don't have to be linear. The velocities could just be the particles spinning. So it could be that these plus charges, or the negative charges, Q1 and Q2, whether they're positive or negative, they're just spinning, and if they spin, they will generate magnetic fields, and those magnetic fields will exert forces on other charges that are nearby. Okay, that's how it works. Okay, so in this example, charge 1 is moving in this direction. It's generating a magnetic field that's going into the board here, and there's another cross product to tell us what force will be acting on charge number 2. And when we do the cross product, we find out that this charge is being pulled towards Q1. So there's actually an attractive force for two charges with the same sign moving in the same direction. If I have two charges and they're both positive or they're both negative and they're both headed parallel to each other, the magnetic effects actually will tend to pull those two charges towards each other as they're in motion. If I switch one of those things, if one of those charges is negative, then it becomes repulsive. If I flip the direction of one of those velocities, that also reverses the direction of the force. Okay, so these things can get complicated. So here's another example. Here's a battery, and we're sending a bunch of current through a magnetic field that we've generated. So here's this piece of iron. It's a magnet. It has a north end and a south end. And what that tells us is, that tells us the orientation of the spinning electrons. So there are electrons that are spinning inside there, and those spinning electrons here are going to exert forces on the electrons that are traveling through the wire. Now, again, the current's going in this direction, and so that means the electrons are going back the other way. But the forces that they experience is due to the spinning electrons that are generating this magnetic effect. Now, the rule here is, this is a cross product effect. I think we wrote that down. Maybe we didn't. I guess the best description we've got is right here. We'll see this. We'll move towards some other slides. But the force acting on the charge depends on its velocity direction and the magnetic field direction that's coming from elsewhere. So there's a magnetic field coming in from somewhere, and that's what's going on here. So these charges have a certain velocity to them. There are charges inside there, and there's a magnetic field direction. And what we find is that the forces are sideways. When we have charges moving in some direction, and there's a magnetic field perpendicular to that, we get a force that's perpendicular to both. Okay, so you can see why we end up with these these right-hand rules. And what they're showing here is an example of that. The current's in one direction, magnetic field is in another, and the force is mutually perpendicular. All right, so here we go. Here are the formulas. Here are the formulas that we can work from. So this is the force acting on a current that is moving through a magnetic field. And the length of the current is L. So the force of a wire, so this is the picture that we were looking at before. And this equation, I think, is set up very well to show how do we calculate the magnitude and how do we determine the direction of the force? So the magnitude comes from knowing how much current we've got, how long is the wire, what's the magnetic field value, and then how is the current direction oriented with respect to the magnetic field. This is in terms of vectors, and this requires us to go back in and remember how cross products work. So we saw these cross products back in Physics 3A and when we did torque. And so this is the same idea that we did with torque. And you may have been thinking, boy, I hope they never show up again, but here they are. So we do have to use cross products to be able to identify where the forces will be when we're looking at magnetic effects. Now the unit for the magnetic field, which if we go back and look at the formulas, is a Newton per amp per meter. We call those Tesla. So you may have heard the word Tesla. Tesla is named after a person, Nikola Tesla, who did a lot of research with a lot of electric motors, electric devices, electric energy transmission, the alternating current power plants that we have. Tesla was involved in convincing people that transmitting electrical energy using alternating current would be much more economical. Anyway, the unit is the Tesla, and the unit, a Tesla of a magnetic field is pretty large. Another unit that gets used sometimes is the Gauss, and that's there are 10,000 Gauss in a Tesla. But the Tesla is the standard unit, and that's the one that we'll typically be working from. Okay, let's see if we can use this formula. We've pointed to it, we've talked about it a lot. So here we go. Let's say that we've got a magnetic field and it's got a particular orientation to it. So the magnetic field is going from left to right in some region. And now what we're going to do is we're going to take a wire, we're going to run a wire through the magnetic field, and we're going to run it in a direction where the direction of the current in that wire is at some angle theta with respect to the magnetic field. Finally, what we're going to do is we're going to go in and measure the length of magnetic field, or the length of the wire that is actually traversing the magnetic field region. So I need to know those three things, those four things. I need to know the magnetic field, I need to know how much current, I need to know the length that the current is running through a magnetic field, and then I need to know the orientation. So let's see what they told us. Yep, 30 amps, that's the current. We measured how far the current is running within that magnetic field, and the length of the current within is 12, oh, it's only 12 centimeters. It's oriented at an angle of 60 degrees, and we got them all four. Magnetic field is 0.90 Tesla. It says how much force, how much magnetic force will there be? So chapter 27, from here on out, we're primarily going to be looking at calculating how much magnetic force is acting on something. And in chapter 28, we'll come back and look at more detail about how the magnetic fields get generated. So here is the force formula. I'm going to say these two formulas are kind of our starting points for determining how much magnetic force something is experiencing. So I wrote this as force with a subscript B, reminding me that this force is due to the magnetic field that is already present. And so I have a current running through a magnetic field, and the force will be the current times. So there's that cross product. Now when we take the cross product, what we get is the magnitude of L times the magnitude of B times the sine of the angle between the two. So in our example, it was 60 degrees, right? That's a theta. The theta value was 60 degrees. The L was 12 centimeters. I, B, plug all the numbers in, right? So everything's in standard units. Now, we've mentioned this also, that once we get into these electric fields and magnetic fields and different types of circuits, we have started introducing a lot of different units. And so at some point you want to be systematic and go through and check each unit so you know how to break each unit down into separate pieces. So the unit on magnetic fields is Tesla. And for me, I think of the Tesla as a Newton per Coulomb divided by a meters per second. And maybe it'll be written down in some of these examples. Anyway, keeping track of the units can help guide you through a problem. But if we put all of these numbers in and check all the units going in were standard units, that means what comes out will be in standard units. And it says the amount of force we get will be 2.81 newtons. Now, there's another example up here. Did I just make that one up? I think I might have. Okay, I did, I think. So here's another example up here where I've got a magnetic field of 5 Tesla and a current of 4 amps and a length of 2 meters, and the angle here is at 90 degrees. And so using the right-hand rule, so what I'm going to imagine is the current represents the flow of positive charge. And so the L vector is defined to be a length in the direction of the current. So in some sense, it almost feels like I should take the vector sign and move it to the current, but we leave it on the L. So that's going to be the direction of the thumb on my right hand. Now this approach is a little different from what's in the book. You're welcome to use what's in the textbook. But this is the approach we used back in Physics 3A when we were looking at torques. And so if I take the first vector, L, which is in the direction of the current, and I put that as my thumb, and then I take my fingers and put those in the direction of the magnetic field, then my palm will face in the direction of the cross product. And the cross product here is the force. And so thumb, fingers, palm facing. And so let's try that. See if it's doable. Thumb needs to be that direction. That's where the current's going. Fingers are into the page, sorry. Fingers are into the page. So thumb is in the direction of L, fingers are in the direction of the magnetic field, and the force is upwards. So that would give us an upwards force. What would happen if I reverse the direction of the magnetic field? Well, then the force would be downwards. What would happen if I switch the direction of the current? Well, that would also reverse the direction of the force. So you can see that we have those different ways of reversing directions. Now, so this is my own example, I guess, that I came up with to be able to show this. Now, an even more fundamental equation would be looking at individual charges going through the magnetic field region. And for that, I just take the charge of an individual charge and then multiply by its velocity. But these two equations are very closely related. So we're going to use this for now. We're going to come back and look at charges later, probably after the break. Okay, now moving down to the problem that they gave to us, We put all the numbers in, we got the force. Now the one thing, well, there's a couple of important things different here. First of all, notice that here, I represented the magnetic field as going into the page. And I used X's to show that. But in their diagram, they had the magnetic field running from left to right. That's fine, not a problem. It's just that we have to have some flexibility as to how we're going to draw the diagrams. So what that gives us is the current is going along the wire. That was the direction of my thumb. The magnetic field is along the page. That's the direction of my fingers. So that's the direction of the current. That's the direction of the magnetic field. My palm is now facing into the wall, into the board. And that's the direction of the force. So the force is going to be into the wall, and that's why I use an X to represent that the force is now into the wall. So with this current going through the magnetic field, with the orientation we've drawn, that wire is going to experience a force that is pushing it back in that backwards direction into the wall. So let's see. We got the force magnitude from here. We got the force direction from the cross product diagram. And that's typically how we do this. We get the direction from the cross product diagram, we get the magnitude from the magnitude formula, and then we put those two pieces of information together and we've answered the problem. Okay, magnitude and direction. Let's see where we are in terms of time. I'm thinking maybe we're getting close to where we want to take a break. Yeah, we're just about there. Let's see what we've got. We could take a break now. That actually seems like a pretty good place to... oh yeah, well let's try one more example here. So the one more example, take a couple minutes. What we've got here is we've got a battery. So I got a battery attached to some wires, and then we're using the battery to run current through this wire loop. And what we're going to do is we're going to drop the wires into this magnetic field region, and we're going to use this to do a measurement of how large the magnetic field is. You know, I know there's a magnetic field there. I'm not quite sure what its value is, but I do have this calibrated circuit, which is, you know, I can put an ammeter here and measure how much current we've got. Now the magnetic field, that's a bunch of circles, and so that's, you know, it's a bunch of targets. And so the magnetic field is coming out of the board on this one. So that's good. I'm glad that we're getting different practice. We're able to rehearse these formulas using magnetic fields in different directions. Okay, and so they're saying that when we do this, we are able to carefully, precisionally measure the tension. So maybe this is hooked to a spring, and the spring is stretched out a little bit, and the spring tells us that this is being pulled down above and beyond gravity. So there's already gravitational forces. But in addition to gravity now, we're getting an additional 3.48 times 10 to the minus 2 newtons. So it's a small effect. So we set up everything, and we calibrate it, we zero everything out, and then we turn the magnetic field on. And well, let's take a look and see what direction the force is going to be in from the magnetic field. So right here, the current is going to the right. That would give me a current in that direction, and a magnetic field, let's see. So the current's going this direction. I'm going to use my thumb to represent a current going off there. And then the magnetic field's coming out of the board, so my palm is facing downward. So sure enough, this direction, this orientation of the current and the magnetic field combined are going to give me a force that's downwards. Now what happens about the forces here and here? I'm not getting any magnetic force here because there's no magnetic field. But once I cross that boundary, I'm going to have magnetic forces here and here. Now what we can show is if the current, you know, is moving consistently in this direction, then I'll have forces downwards through this length between A and B. But when I turn the corner, the forces now are going to be oriented to the right. And on this side, let's see, down, out, the forces here are going to be outwards. So force out here, turn 90 degrees, force down, force down. It's still outside of that loop. And then here I'm going to get, so check those. You know, practice with the right hand rule and check and make sure that you can get the directions of those forces correctly set up. So the forces here will exactly balance the sideways forces here. So these two forces are certainly present, but they're going to cancel out. So the net effect from the magnetic field is going to be felt along just that stretch right there. Now I'm hoping they told me the length from A to B is 10 centimeters. So just this length, the one that we need, is 10 centimeters, and they've told us how much force. So that means we can plug this back into that very same formula, right? Now, we already did all the directional information, right? We went through all the directions needed to verify that the force was downwards from the magnetic force. Oh, here it is. The magnetic forces are downwards. Here they're sideways here. Here they're side. So here's all the directional information from the diagram. So once we've established that, then all we need is the magnitude. Now the angle between, in the formula there's an angle, it's the angle between the current and the magnetic field, and the current's going here, and the magnetic field is coming out of the board, and so they're perpendicular to each other. That would be 90 degrees, and the sine of 90 is 1. With these cross products, it's when the two vectors are perpendicular, we get the biggest effect. And that's what we're getting here. So since this is a factor of 1, I can just drop that. And the force is going to be at its maximum value, ILB. Now, we're actually solving for B. So I'm going to flip the formula around and say the magnetic field must have a value of given by F divided by I divided by L. I put all those numbers in. They're all in standard units, which guarantees the answer will come out in Tesla. And we've just measured the magnetic field. So it's going to be 1.42 Tesla. Okay, so that is a good place to stop. That kind of carries us through the first part of the chapter. So let's take a break for 10 minutes or so.